Good morning, Henrik.
Good morning. Hi, good morning.
How are
Okay, so starting with a small recap, I talked about the profile evolution tool last week. So zooming a little bit into modeling cross-shore transport and the related profile evolution as where we could really see and model the changes of the water depth as a position of I felt that from the audience, from your questions in the audience, there was still some confusion around when is it profile tools, when is it lit line, etc., etc. And Samir, of course, also answered that or tried to answer on that. And I guess also by now in your hands-on exercises that became much more clear. But yet, following up on my last presentation, I want to start with a small overview of the LitPack models. Once again, there will be some pictures you've seen before. I know that Samir also used some of these same diagrams, but I'll try to also arrange it one more time, and then hopefully we all aligned on where what is applied. And then in the second part of my presentation, we'll be looking at 3 projects, all in Denmark, that we delivered in the recent past with different components of the LitPack modeling suite. So that's the agenda. So the first part, the LitPack modules. But let me allow to one slide on general modeling comments. So that would be applicable for any modeling exercise, because I also felt that there was some questions from the audience going in that direction. Okay, what is it actually that we then get out of it, and why is that model assuming this and this model assuming that? So in that context, I think it's valuable to recall that fully resolved numerical models, they only exist for very, very small problems. So for example, there's a direct numerical simulation in CFD. If you Google the literature, you can get like the flow around a sphere or something like that, where we really try to resolve exactly the physics of what's going on. But that's only very small problems that are not really of much use directly, at least in the real world. So that means that for engineering application, simplified design tools and numerical models must be applied. And that's actually the category where the whole LitPack suite is in. It's a set of simplified models, and these models are often built for isolated processes. So I cannot model the whole real system with all its interdependencies, because then the model becomes way too complicated and I can't run it for long periods of time. So I isolate, or we isolate processes, and then often we develop models, individual models for these isolated processes on benchmark problems. So for example, refraction of a wave or shoaling of a wave. And often that is based on benchmark problems from controlled environments, meaning from laboratories or maybe from short-term observations in situ. For example, laboratory, again, maybe a regular shoaling of a regular wave over a slope is one of those examples. So a very isolated a process for which then a model is developed and a theory is developed, and we now also use that theory. But when we then apply those models to the real world, and that's what we're doing in this course, that's what that course is all about. How can we use the LitPack modules in the context of coastal management and coastal design? When I apply those models to the real world, there will always be simplifications. And furthermore, we will, to some extent, violate the model assumptions. So in the beginning of the manual, there's always, for example, the profile evolution tool we looked at last week, the assumption of a uniform beach, and that one profile can describe the contours along that entire uniform beach, perfectly parallel contour lines, that would mean, and uniform offshore hydrodynamic conditions across that beach. And you will agree with me, when I take that model to any beach in the world, we will be violating that assumption because the contours are not parallel, because the hydrodynamics, the waves, the regional currents are not uniform along that beach. But what does that mean? Does it mean we can't use the tools at all? No, of course, that doesn't, as you know, that's not the message. The good news is the models can still be very useful and powerful tools. However, it is then the engineer's responsibility to choose the best method and the best models, considering the few thoughts that I put here, a few bullet points, the available data, the available tools, the project objective and risk level, and the time and budget. And of course, it should be all related. So, for example, you might be doing a preliminary design. In that preliminary design, usually you don't have a lot of data available. There might not be in situ wave measurements. So, because it's a preliminary design, your time and budget might be smaller. So you might only have the tools available that are available to you in your company wherever you work. So, but then it's only a preliminary design, so the risk level is also lower. So that means, okay, it's okay. So you go through a first modeling iteration, just knowing that probably the mistakes you're making are quite large. So your confidence in that is quite low. But for a preliminary design, that can still be sufficient to do some strategic decisions, maybe to initiate modeling campaigns, to initiate sediment sampling on the beaches, identify the profiles you want to model, etc. And then you go back for a detailed design and you do a more a detailed campaign with a larger time and budget, for example. So it's the engineer's responsibility to make good choices here. And then the second is then to understand the simplifications that have been made and account for them accordingly. Example, preliminary design, maybe very limited input data, maybe very rough model, maybe you only modeled a year instead of 10, whatever. And then you just need to also communicate that and maybe allow for it with sufficient conservatism. So that's just to set the context a little bit of, yes, we have many powerful tools within the LitPack modeling suite, but they are for different components, and we will always make some simplifications, and it's us as engineers, as modelers, then translating that into actual design decisions. And often in coastal engineering, actually also with a good monitoring program following the project implementation. That's also crucial because there are high uncertainties in the coastal design and coastline management, even after the detailed design phase. So usually there will be a monitoring programs to be designed, and then it can be followed up, etc., etc. Setting. So yeah, that's a bit the context. So keeping that in mind, we can have another look at the LitPack modules. And I think Samir has also used these diagrams here from an old LitPack documentation you can find on the internet from published by DHI. And the sort of the structures and the names that have changed a little bit since this was published, but it can still be used and put into context of the current organization of the LitPack toolbox. And by now, you will know most of this. So it's, as I said initially, it's also a little bit of a repetition. So we have the one key component is the longshore and cross-shore sediment transport in a point, the STPQ3D, the, what was it again, semi three-dimensional transport in combined waves and currents. So that's, as it's indicated here, this gives us a vertical, it's a vertical model in one point using non-linear wave theory to model the flow field here, and then applying models to do the suspension, to model the suspension of sediment depending on the forces on at the sea floor, and then the transport of bed material and suspended material. And that the input to that model are the hydrodynamic conditions, so wave height, period, and regional currents at this point. And then that same model can be called at this point, etc., etc. So longshore and cross-shore sediment transport in one point. That's the one component. And it can actually also be called, I think I said that incorrectly in one of the sessions, it cannot be directly called from the toolbox, but from the littoral model FM, it's actually that first point here. So it's usually not in applications, we don't do that. But if you really want to dive into maybe the calibration of that point, or it's mainly for theoretical and investigations, you can actually model the transport in one point. And then here at the, sorry, why does, here we go. Then here at the bottom, we have the profile evolution displayed. So that's that tool that can be found in the LitPack toolbox. And the profile evolution models the cross-shore transport, so indicated by the white, two white arrows here. And then the profile evolution due to the variation in cross-shore transport. So we can see, for example, like that black dashed line here, if we say the yellow profile is the original profile, we can model how that black dashed line here develops. Maybe a bar is developing, etc., etc. And this model here includes the shallow water wave transformation due to reflection, shoaling, and breaking, and its effects. And the effects are the radiation shear stress driven longshore, current, and the water level setup. And this model then has a hydrodynamic model to model the hydrodynamic conditions along the profile. It then at each point calls the transport in a point. It then has the cross-shore transport. It does an evolution step of the profile, and then it goes to the next time step. And then there was that little small thing with the table generator. Instead of calling this transport in one point model all the time, which could be done, but it would be computationally expensive, we can tabulate these hydrodynamic conditions and the transport associated with them. And then here on the other side, on the right, we have the littoral drift along a uniform beach with arbitrary coastal profile. So that's the guy here in the littoral, in the LitPack FM, the second point, the littoral drift. Again, we have a hydrodynamic, we input a profile, we have a hydrodynamic module, the same hydrodynamic model as in the profile evolution, which resolves our hydrodynamics across that profile. So again, including shallow water wave transformation, refraction, shoaling, breaking, and its effects. Then again, we call the transport in a point model, and we get the transports, but then we don't do the profile evolution. We don't change this profile. All we compute is the potential, and that again is important. We also discussed that before. We compute the potential littoral drift in different conditions. And while in the littoral drift, we only can compute the potential littoral drift. So we don't look if that sand is actually available. In the profile evolution tool, we discuss that include non-erodible layers in the profile. And if the profile hits that non-erodible layer, or also structures can be included, like a submerged breakwater, we looked at that, then the profile doesn't further evolve. The littoral drift, we only look at the potential transport. And then we have the coastal evolution. So that's the bottom button here in the LitPack FM, where we then, due to a variation in longshore transport, so if we have a couple of those profiles and there is a difference, a total longshore profile, we can then look at the coastline evolution, how it changes. And actually, there's a little bit of an inconsistency in terminology here, I think, because also in the shoreline management handbook, also by DHI, there was they distinguished between coastline and shoreline. Shoreline being the waterline, let's say, and coastline being between the beach and the dunes or the hinterland. But the book also mentioned that, I'm referring to my first presentation. The book also mentioned that coastline is sort of commonly also still used for shoreline. And that's also true when reading through the literature. So we need to always pay a little bit attention to what we're actually talking about when we use the coastline term. And additionally, in the coastline evolution, we can then also, I mean, it says along it's variations in longshore transport and from these profiles, and we again assume a uniform beach. So the moment we have something like this, a harbor here, for example, we don't have a uniform beach anymore, right? We violate that model assumption. But for a small number of structures within certain other conditions, the coastline evolution tool actually includes submodules. So a small number of structures across the beach with local effects, as well as sinks and sources, for example, a river outlet, they can be included in the coastline evolution. However, larger structures that would lead to complex current profiles or complex currents around a headland that long exceeds out of the breaker zone, that would be outside the capacity of this coastline evolution tool. So that's a little bit the overview. 2 more slides on the profile evolution versus littoral drift before we come to the project examples. And what I want to output is a little bit more what exactly is, or highlight a little bit more is what is happening. How is a profile evolution versus a coastline evolution, right? If I model the coastline, then something also needs to be happening with the profile. So how can then the littoral drift have a constant profile? That's what I want to highlight here in the next 2 slides. So profile evolution, again, one can say it's the depth. So the output is the depth as a function of x and time. X in the profile evolution is in the direction of the shoreline normal, and I can model something like displayed here. So the initial profile and profile after 4 weeks. So it's really like the water depth as function of x and t changed completely. So I could model like this example again from Australia. I showed it in my other 2 simulations as well. I could really try to model how this bar disappears after a storm event, and how then that post-storm profile approaches the average profile again. I could try to model that with the profile evolution tool. In the coastline evolution, on the other hand, we actually assume a beach that's sort of parallel to a baseline, and then the y direction is the shoreline normal. So x and y is also is swapped now. And here I model the position of the coastline YC, or here in this image actually Y. Both are from the same manual, so always careful when you read figures and in text. But I sort of model the position of that green line due to the change in the littoral transport. And the cross-shore profile at a given position is kept constant. It's only moved back and forth in they call it a one-line approach in the direction with the coastline evolution and given the position Y. And that's indicated here. So there's a delta Y here where I'm pointing at now. So we input a constant profile, and then depending on the on the differences in long-shore transport. If I have a deposition here or an erosion, then I just move this profile back and forth. And then in the next time step, the hydrodynamic conditions are computed, inputting the offshore conditions slightly at a different position. But I'm not changing. I'm not developing all of a sudden a bar as we can do with the profile evolution tool. And that sort of just means that we're sort of looking a little bit at different time scales. So of course, I'm making a mistake when I use this profile evolution tool and there is and I model maybe 40 years and sometimes there's a storm, a bar developing, and then the bar is disappearing again. Because while there is a bar, there's probably the littoral transport has a maximum at the bar, whereas in other conditions, it's more evenly distributed. But as long as this profile here in the that I assume is sort of the average profile, it probably doesn't matter so much for the long-term coastline position if now the littoral transport happens a little bit further offshore, a little bit further nearshore. So in the context of long-term modeling this coastline profile evolution, I can accept that the acute erosion in the cross-shore profile direction is not resolved properly. And why is that done? Well, it's done that. Why is it separated like that? It's because we have highly efficient modules for the two processes, right? Both models are relatively fast. If we then again, it's for the engineer to judge if that's okay to look at these processes individually. If we expect that there is interdependencies, well, then we might have to choose another modeling approach, or maybe assume individually different profiles here and run multiple LitPack, LitLine modules, etc., etc. There are some options there. So these are the basic two differences. Hopefully, maybe that in combination to your discussions also you had with Samir, which I of course didn't follow. So I hope it was not too much double up now, but I hope it made a bit more clear what the difference is between the profile evolution toolbox and the LitLine, and how the profiles are handled, the cross-shore profiles are handled in the two respective packages. And with that, we would go to some project examples. And I came with 3 projects from Denmark. And the first one is, I didn't spend time on now pinpointing where they are exactly, and you also will not find detailed results, of course, but just giving an overall high-level picture of what was the scope and how was it approached. So the first one is, it was called nature-based flood protection. So in a municipality, in a Danish municipality, in one of the inner Danish waters. So when I say inner Danish waters, there's the Baltic Sea, right? West of Denmark, you have the North Sea, which is connected to the Atlantic, or part of the Atlantic. And then on the east of Denmark, you have the Baltic Sea, which extends around Sweden and up to Finland, etc. And we are on the east side now. So it is an enclosed sea. And the idea here was to establish a beach dune system as flood protection. So there is some sort of beaches and dunes here still available, but to sort of extend that. We already discussed that. If that can be established, it's a very effective measure to stop shoreline and coastline erosion, because the dune acts as a natural reserve of huge amounts of sand. So if you have a storm event, the dune would be eroded, and the sand would be additionally be available to form offshore bars. And then over periods of calmer conditions, the bars would be the beach slope profile. Sorry, the cross-shore profile would become milder again, and sand would be deposited on the beach at lower water levels, and then wind would carry that sand back into the dunes. So if you can establish a balanced beach dune system, that's a really powerful coastal protection system. So the main goal here was to assess the longshore sediment transport and the coastline evolution. The modeling approach was the Mike 21 spectral wave model to establish the wave conditions. And that's also, as you will see, almost an integral part of the LitPack modeling, because it is the most important input parameter, the wave conditions, that's driving your sediment transport. So if you're not supplied sufficient wave data, you will have to also usually establish that yourself. That's at least the case in most of the in most of the projects we are dealing with. And then we use the littoral process, FM, the littoral drift and the coastline evolution. But we also use the profile evolution tool to then assess some characteristic storms, how that would impact what the acute erosion would look like. And here two more images on the scope. That's sort of what it looked like at the starting point, and the idea is we will see the original coastline in a second. But this is sort of what then after our input, the final result was, how the landscape architects established then the new beach line based on the modeling results. So here we see the coastline in the inner Danish waters. We decided on we needed to decide on the SW modeling domain. Here we have there's only a small open boundary here and a small open boundary here. So it's in terms of waves, it's only wind-driven waves. So we didn't have to include any offshore boundaries. So we would just model the wind-generated waves with the SW model, and then have a fairly high resolution around the area of interest. Translating that to conditions in Egypt, to the north coast, especially the Mediterranean, the exercise of the SW modeling would be to transform the offshore wave conditions in very deep waters to coastal wave conditions. So still in a domain where nonlinearities are not dominating, so that the SW model can still handle it, but it's usually still a higher resolution than any available models in the resolving the entire Mediterranean model, Mediterranean Sea. And then from the high resolution, you would also usually include locally available bathymetries. So there, where the mesh is highly resolved, we're also resolving the conditions around the area of interest. Then you need to choose profiles, and this is now what it looked like before the project was developed. And this is, of course, again, not it's not 100. It's the coastline as a general is not 100% uniform, right? We have here a long breakwater with a steep grading in the beginning. It's at profile 3, right? It's actually a hard structure, so it cannot be eroded. And the profile 1 here, all the way in the bottom, we have some dunes inshore. So of course this down here is very different from this one. But each of these 3 profiles, and that's why 3 profiles were chosen, are sort of representing one of these shoreline sections. So they have different characteristics, and that's why these positions were chosen. The one is the orientation, right? These three are sort of linear. We can draw sort of three lines with their three characteristic orientations. And then the other difference are the profiles themselves. So how steep the slope is, and then also here in the north the structure, as I said. So this is already one step now. This is already one engineering choice that we need to make, right? What is the situation? Where do I need to place profiles? And sometimes it's actually iterative. And the second thing is then, after you've chosen where to place the profiles, how long should they be extended to offshore? Because in the LitPack model, we will input the offshore wave conditions from the SW at the starting point of the profiles, right? And then near shore, but that we actually discuss a bit further in my last project example, because it's a good example to discuss that component. But anyhow, we input the offshore wave conditions here, and then some nearshore wave shallow water transformation along the line is taken care of by the LitPack module FM, but no 2D effects anymore, right? So we have refraction, shoaling, and breaking, yes, but we don't have any diffraction along that line. So if parts of that profile is much more sheltered, so for wave events, for example, coming from the south, maybe the last part of this profile would be actually affected by some diffraction around this little headland. If I input wave conditions here, that will not be displayed in this one here, in this profile. On the other hand, the water here might be very shallow, and the SW model might be showing some diffraction, but it might actually not giving the correct wave heights because other effects are not included in the SW model. So whatever choice we make, there might be some small mistakes which we need to be aware of. Then we get the longshore transports out of the littoral drift module in the different profiles. You will by now have also seen some of these results, but just as a recall again, we get the plus and the minus. So then you just need to think about, and even I don't recall it now top of my head, but for that you have the manual. One will be then northwards and southwards, because the profile always starts at the offshore point, right? So this is the red and the turquoise lines are the transport in the two different coastal directions. And the blue one is then the difference, which is the net transport. So again, that would be the one relevant for coastline evolution, because that's what on average is transported in the one or the other direction. So the net drift has also a direction. And then there's a gross drift, which is the sum of these of the absolutes of these two components, relevant for backfilling of channels, for example. So we get that in the three profiles. And then one important component is to try to ground truth your model results. And unfortunately, in coastal engineering and sediment transport, that's often, or in sediment transport, that's often qualitative comparisons, because we can't directly measure sediment transport, right? If you set up a wave model, you might be lucky and have a wave buoy, and you get concrete measurements of the significant wave height, for example. Then you have a quantitative measurement which you can compare it against. With the sediment transport, that's a bit different. So for this third profile, where we have the pier, this hard structure here, where the water depth goes from about -2 meter steeply up, we have the we have a very large transport and almost no transport along the other profile. And if you get such a result, you could try to verify that. Is that true? And one option is to look at images from a site visit, to talk to the locals, to look at satellite images. And here the conclusion was that yes, that is true, because there is, you can really see a sand plume in the water column very close to that structure. So it is true. If the profile wasn't as steep but more a milder slope longer out, then this was what would be a different picture. So although there's not direct measurements available, there is still other means of trying to verify that at least qualitatively our models are correct. And then of course you can also another check is if the sediment transport goes in the right direction. It will be from the port authorities or the locals or whatever. There will be some information available in what direction this plume is usually going. So if your model shows that that plume is also going in the north direction here in this case, then you're on the right track with your model. If that's not the case, then something is wrong somewhere in the setup. So it's always good to try to make these comparisons. And then the next step was for these two profiles here, because it was out of scope to change this pier. And here again, the plume can actually also be seen. For these other two sections, the equilibrium orientation should be found. And that was done with the littoral drift module. And then we came up and we looked at that before, the Q alpha curves. So you basically change the orientation of your coastline here, given the wave conditions, the offshore wave conditions, and then you find the coastline, the theoretical coastline, the equilibrium orientation. Also here you can again see that you start making some simplifications, because when we change this profile, the model still sees, when we change the orientation at that profile here, and we rotate it down here in this point, and we're of course going out along the bathymetry lines, and we still assume that then this profile will be moved. And that's of course the assumption that after we've established this beach here, that is correct, that then somehow these profile lines here will be established as they are established here. But if that's entirely correct or not, that's also not necessarily known at that stage. So that just needs to be again communicated and maybe reassessed at a later stage. If we rotate a shoreline like down here around this point of the profile, and also if the changes are not very large, it's probably a minor error that we're introducing with the water depths along that profile. And then after these, I go one slide back. Sorry. After these orientations were established, they actually then informed the decision to where the beach dune system should be established. So now, then this is the next sort of developer drawing where these orientations have been adapted. And then the next question was, there should be two groins or three to have established two beach sections and to optimize the beach stability. And then the question was, how long should these be? Because as you remember, the equilibrium orientation is on average, but of course you can have single events which come quite from a different angle. And during those single events, you can have transport, as the model also shows, but in the time evolution, along the shore. And the idea of installing these small structures is then here in these events, keep material as much as possible inside these beach sections, as then more normal conditions establish again, or conditions from another direction, this coastline here can reestablish. So that was the objective in that next step. And the way that was done was, after now these profiles here existed, the coastline evolution tool, sorry, that was too fast. The coastline evolution module was used, and the structures modeled with these empirical formulations there. And then again, this was an application where the model formulation in the coastline evolution structures part was made for, because it's sort of semi-empirical formulations of some sheltering effects, etc., etc. If these structures became huge, maybe way exceeding the breaker line, or if there were too many, that the sort of re-establishment of longshore transport some certain distance below along the shore from the one structure we have already the next one, then we would violate the model assumptions too much, and we could not use this tool. Or maybe there's actually a little trick in the described in the menu, that if you have a large number of cross-shore structures, then you can actually, instead of modeling these as cross-shore structures in all these points, you can also model the global effect with the longshore structure. So there is some tools available to use the coastline evolution module, even where we have interruptions of our littoral transport due to structures, so we don't have that uniform beach anymore. But we just need to really recall that for what context these available models of the different structures are made, and what exactly the constraints are. And if it really becomes too complicated, there is then at some stage, of course, the point where we outside what can be done with the coastline evolution tool. And actually, there's an example of that also in the last project I'm showing. And in that case, maybe we can still use other components of the LitPack model suite, or maybe sometimes it's so complicated that we simply have to find another model altogether. And then finally, the next step is then to assess the acute erosion with the profile evolution tool. And that's now exactly the example that we discussed before, where we independently look at the longshore transport and coastline evolution, where we keep the profiles constant and move them back and forth along the position or the distance from the original coastline. And that's probably true on average. But then the second question is now, okay, looking at storm events, so more short-term in time storm events, how does the profile respond to that? And for that, there were, in that case now, 3 storms selected with a slightly different direction. The initial profile, and then the response to those 3 storms in green, blue, and red. And then actually here the same was done once in 2020 as a reference year, and then also in 2070. So in that case, assuming some long-term sea level rise. So the design water level in that case will be higher. So we're seeing the erosion due to otherwise same storm events happening at a much higher elevation of the dune. And the takeaway of then these assessments is that what is, for example, if you take the blue storm here, what is eroded here is deposited down here. So that means it is still available again for re-establishing the cross-shore profile in milder conditions. So the sediment is still available for the longshore transport after the storm event. Only that then for some time the longshore transport will be happening a little bit further offshore. But if then that sediment down here is transported along the beach a little bit and then deposited further near shore again, for the overall mass balance in the in this coastline evolution models, it doesn't matter, right? So let's say that here's a piece of sand where I'm pointing at now, or like a little unit of sand. And in normal conditions, it would be transported along the beach like this. But if I now have a storm, it's deposited down here, and then it's transported along the beach like that, and then it's coming back in normal conditions. I also end up here, right? So then the longshore, the long-term effect relevant for the coastline evolution is the same. So that is why it is in that case applicable to model it, or it is possible to model it in these separated approaches. When would it then not be applicable anymore? When would our coastline evolution approach be not applicable anymore? Well, that would be the case if the storms have an impact all the way to lower water, and what is deposited here might not correspond to that anymore. So this green storm might be a little bit on the edge, meaning that large amounts of material are lost to offshore. Because if large amounts of material are lost to offshore, they cannot be transported along the beach anymore. They cannot be reestablished anymore. So, and then it's up to the engineer to now judge how often do we have storm events where large amounts of material are lost to offshore. So these events might have a significant impact on our coastline evolution, or are most of the storm events sort of small and just the position of the bars changes a little bit further away, a little bit closer, but overall the longshore transport will not be affected by that. And an additional component to that might be that this beach might be in the future also actively managed. So there might be some ongoing beach nourishment exercises, and then this assessment would be a component of that plan. Like what is the probability distribution of these storm events where we lose huge materials every how many years do we need to come to repeat beach nourishment, or do we not need to repeat beach nourishment at all because the dunes can take care of that themselves? That are the sort of questions. But again, we will then come up with answers to those questions during this modeling campaign here, but still need to be aware of that we will likely have made mistakes. There will be mistakes in this whole modeling chain. It started with the spectral wave model. We use atmospheric forcing. In that atmospheric forcing, maybe the islands were not resolved correctly. So we don't have the winds 100% right. So we don't have the waves 100% right. We might not have the bathymetry 100% right. So there's all these accumulated errors. For some of those errors, we try to quantify them by sensitivity studies, right? You sometimes just run your model with slightly modified parameters. For example, you can say, okay, what if my significant wave height is 10% higher? I run it again, and then you get a quantification of that potential error, right? You can do these exercises, but still, you will probably want to establish a monitoring program after this beach here, after this has been established, and then long-term compare your results with what is happening in the real world. And if you already after 5 years, after 2 or 3 years, can see that there is a huge difference between your initial assessment and what you're seeing in the real world, then you might want to assess that. Maybe there were some storms that you did not account for. Maybe whatever. Maybe your sediment sizes were different after all. So this initial design and the modeling in a coastal management and coastal design context is often only one part, is the initial part, our best possible estimate, which then should be followed by a monitoring program. So it's quite different from other engineering disciplines, right? You can clearly see that by now. Let's say design of a bridge or whatever, where where way less uncertainties exist, where design standards for that reason exist, etc., etc. That was the end of the first project example, and I think I'm sort of halfway through my scheduled 1.5 hours of presentation. Samir, should we take a 5-minute coffee break before we look at the last 2 projects, or should we just carry on?
Okay, I prefer to take some break for 10 minutes. It's okay.
10 minutes. Okay. So we meet again in 10 minutes. Thanks.
Okay, thank you.
Okay. I was just seeing people still talking in the room, so I wasn't sure. If you don't mind, maybe you can mute again, so I don't have the echo. Thanks.
Okay.
So there's two more projects I wanted to have a look at with you, and both also in Denmark. So the next one is a beach nourishment. So of course similar to the first one, but in this case there is no establishment of a new orientation planned, and also not possible, as we will see in a second. So the scope again is to assess the longshore sediment transport and optimize the beach nourishment, and to assess the acute erosion of the beach nourishment under storm conditions. So again, the separation here of long-term, longshore, short-term profile evolution. And the modeling approach, again, also similar. We need wave conditions. So again, we need to set up a spectral wave model. We use the littoral process FM with the littoral drift and coastline evolution. By the way, we of course also use the table generation in that step here, right? The moment you do coastline evolution, you have to generate the tables. I didn't mention that here specifically. And then the profile evolution tool, where also tables are needed, but that's by now just an integral part of these models, right? So SW model here on the left, converting again more offshore. It was still actually a wind-driven sea in these inner waters, converting the wave conditions to intermediate water depth. And then a second one here, which we also did in the other project, but like a general one, is also usually that the mid-ocean conditions then have to be analyzed, and we need to come up with the design values for the storm conditions. The long-term longshore transports are usually generated with time series, long time series, or maybe statistics of which wave direction and wave height occurs how often. Usually we do it with time series, because then you just have the water level time series also as input. But then for the storm conditions, you need to define design storm conditions, right? Your significant wave height and your surface elevation. And if you have 2 time series, one of significant wave height and one of surface elevation, you can do an extreme value analysis on these 2 individual variables. But very relevant for our coastal applications is the joint probability. And there's different methods available, and also certainly not the topic of today's course. But we need to know, you can have in this case here, for example, if you then want to define for the, let's say 50 years, this second last contour here, you can get the highest significant wave height above here in these conditions around ±0 water level, and then you can get the largest positive water level with a fairly small significant wave height, and the other way as well. So when you then, and that's given by the meteorological and hydrographic conditions of that location. So if you then need to, if you are asked to assess the profile evolution for a 50-year event, you might have to model different scenarios of a 50-year event, because there can be, a significant wave height of the maximum significant wave height, but with no positive water level. It might be less severe than a slightly smaller wave height, but with a larger water level, because your transformation of waves then in the shallow water can go much further up the beach and possibly even erode your dune. Usually there's a positive correlation between large wave heights and large water level, because usually you have storm surges that correlate together with large wave events, but that's not always the case. You can, in some areas of the world, have independent water level setups that are driven by other effects, seasonal variations, whatever. So looking at doing some statistics of these mid-ocean conditions and designing your and choosing your design values for your coastal modeling is also another integral part of this exercise. And maybe you're not doing it yourself, but then at least you need to request these inputs from others and then also understand what that is and challenge that, etc., etc. Then again, we're looking at this sort of beach, and then here we chose two profiles. A little bit of Danish here now, because it's a report that, of course, was delivered in Danish. But there is one profile here and one down here. So the differences here, why that now was chosen, is that there is, as you can even see on this aerial image, there is obviously variation in contour lines, right? It's much more shallow here than it is here. So a much milder slope here at location B. And now we need to sort of do some engineering judgment, how, so it's not strictly uniform, the contour lines going to the south. How many different profiles do I now need to model where that will be relevant? So, and then also not too many profiles where then all of a sudden maybe our model results suggest some accuracy that's also not present. So here, that's then where experience, discussion with colleagues, etc., comes in. We chose in that instance two profiles to assess, and then here the dashed blue line is then the existing profile that we established based on available terrain data and available water depth data. And maybe there is a gap, maybe you need to fill it in with some local knowledge, etc. And then the idea is to assess the beach nourishment. So if additional sand material is placed in a profile like that, so it was assumed that a new sort of a new dune land will be established, and then just a constant slope to below the water line where it's hitting now then the existing bathymetry at this point. And then we want to assess the longshore transport of such a beach nourishment, because that beach nourishment is established in a fairly short amount of time. If we then place that, how will that develop? So that was one of the scopes here. And the other scope was the acute erosion with the profile evolution tool. So now we can see here in blue is the profile after establishing the beach nourishment. And here's two of these design cases. And we can see that there is a huge difference in water level for these two design cases. And that means with the high water level, we get an erosion, but then a bar developing on the beach nourishment itself, which will then probably also reestablish itself. But then for the low water level storm condition, we actually get an erosion of that beach nourishment at the bottom, and which will sort of erode the base of that beach nourishment. So this is now assuming that these storm events happen immediately after the beach nourishment has been placed, or if the beach nourishment, depending on its what grain sizes we choose for that, it also has an equilibrium profile, right? So then it would be placed quite close to the equilibrium profile. So assuming that long-term conditions at the site will not change this too much, but then looking at the storm conditions, we can expect something like this. And the second component, as we discussed, was including such a beach nourishment. So again, now the profile here is already placed, including this additional amount of sand. What sort of longshore transport do we have? And we again have these curves here. Displaying that where the highest longshore transport is to be expected, and that's actually the sort of averaged over or accumulated over the simulation period. So that's not a snapshot at a given point in time, but over the assessed model period. And then we also looked at the Q alpha curve again to establish the equilibrium orientation. And we have the brutto transport and the net transport. And for finding the equilibrium orientation, the net transport is relevant, which is the blue curve here. And it has a direction. So the transport can be negative or positive, meaning going in the one or the other longshore direction. And here in dashed is the 0 line. Now we have the 60 degrees is the current orientation of the coastline, and then computing the transport for angles at in the range of plus minus 45 degrees from the 60-degree coastline. And what can we see on this blue Q alpha curve here? It's quite different from the Q alpha curves that we've seen so far. And I'll resolve it in a second, but you can think about it for yourself for a moment. So what we see is that for all angles plus minus 45 degrees from the current orientation, the netto transport is negative. So it's not changing direction. So it means we don't have an equilibrium orientation available at that beach with plus minus 45 degrees. It sort of seems that it's approaching 0 here, and if we continue, then it might cross 0 at some stage here. If we really orientate, here we 10 degrees, right? This beach here, if we just go back to here, is at the moment is at 60 degrees north, and at 10 degrees north, I mean the beach is rotated by 45 degrees. Then we may be approaching something like an equilibrium orientation. But that basically means in this in this situation, we cannot achieve a stable beach. So a beach nourishment will always only be temporary. It will be transported along the beach and lost eventually to outside the project area. Sometimes if the difference between the coastal orientation and the equilibrium orientation is small, we also discussed that I think already, then with small structures with groins, I can change, because then the sand is accumulating on the one side, I can change the orientation maybe by 10 degrees or something like that. And I get these sort of these sort of zigzag coastal profiles where then each beach subsection actually develops a stable beach or in the equilibrium direction. And then maybe with groins, I can actually stabilize my beach. But that's not an option here, right? We will all agree we cannot rotate with any structures. With any structures, we cannot rotate the coastal orientation by 45 degrees. And then after that step was done, we also did a little bit. We did also coastline evolution. So then there is a chronic erosion, as just discussed. Even like there is a chronic erosion now, so long-term erosion, and there will be a chronic erosion after the beach nourishment. And now, as coastal engineers, we can only sort of assess if it can be reduced a little bit. We can, so again, place small structures which can be modeled, or in that case, in the coastline evolution with these point structures, and then having local accumulation. The local accumulation and erosion effects are parameterized in the within the coastline evolution module. So we can assess the impact of small structures, and if we can with that have a positive effect on the coastline evolution and maybe prolong the life of one beach nourishment. But yeah, that the result here so is then with the client or with the local community to establish that in the given conditions the beach cannot be permanently stabilized. So beach nourishment is going to be beach maintenance, and maintenance has to continue in the future. And then these plans can be established to also assess the financial impact of it. Every 5 years, whatever amount X needs to be placed. So there can be a long-term planning established. And already that can be a large value, right? Compared to being completely in the unknown. Coming to the last project, coastal protection with the so-called sand motor. The first one, the biggest one and the most famous one is placed in the Netherlands, and I can really recommend to you to Google sand motor in Holland or sand motor in the Netherlands. Will find a lot of interesting videos and also research material, because it's established by or paid for by the public authorities in the Netherlands. So there is a lot of cross industry collaboration and a lot of material available. But the first one was to be established also in Denmark on a way smaller scale. So the idea of a sand motor is that you place a large amount of sand in one location, and you utilize the longshore transport to distribute that along the beach. So it is in a way also a beach nourishment, but just on a applied in a different way. And this is the site. It's placed again in the Baltic Sea in Denmark. And by now you can see from the 3 examples I brought here from Denmark, we always have blue skies and always the sun is shining. There's no strong winds and no rain in Denmark. And the scope is to assess the efficiency and optimize the position of such a sand motor, which, by the way, was also proposed by the local community. And I included that here because that's another interesting component of an important component of coastal engineering, right? The socio-economic component. So here in that case, in Denmark, climate adaptation is a huge topic, and a lot of local communities, they live there. They know what's going on. They, in the end, have to pay for whatever is established through a taxation scheme in Denmark. The local landowners, they will over the next years have to pay a certain proportion of the coastal protection measures. So that means that the municipalities, they often have some discussions and some ideas of what should happen. Some municipalities are further advanced than others, but then as an engineer, in that case, it was a clear assignment. Actually, that local community was paying us to assess their proposal and also look at alternatives. But even if that's not the case, it pays off to work with these local communities and to use also their knowledge And also in the end, they need to accept the whatever solution you come up with, right? If that completely, let's say, destroys their value in the coastline, then you might be protecting them in some engineering way, but the value for them is limited in any way. So it's a bit of a sidetrack here. I know it's not LitPack modeling, but it's another very relevant and interesting part, I find, of coastal engineering. So the scope was to assess this efficiency of a sand motor that they came up with, and also respect that suggestion, even if it then maybe proves not to be a good solution. Still respect that suggestion by non-professionals, and then also to propose other solutions. And the modeling approach was again setting up a spectral wave model, and then we used from the littoral process FM the littoral drift. In that case, we didn't do the cross-shore profile evolution, and we also didn't use the coastline evolution because it was here really outside of what could be modeled with the coastline evolution module, and we will look at that in a second. Why that is. So this is a top view, and the idea, there's sort of two coastlines with a very different orientation on the tip of this sort of peninsula here, and the idea is to place a sand motor in this area here, which is then transported over time along this beach, and then of course also has to be refilled from time to time to stop the chronic erosion here along that beach. And you can already see there's a number of groins here installed, actually many, and you can see how the orientation of the coastline changes between those subsections of the beach, but that's of course always only a snapshot. So this can look different after the next storm. So this is really a snapshot of this satellite image taken after whatever conditions were prior to that image. The first step was a site visit and a dialogue with the locals. As I already mentioned, it's a very crucial component in this project, and you can see there's a lot of small structures along the entire beach. There's some sort of revetments with stones, like not hard engineering structures of concrete, but like there has been a lot of activity already in the past, again driven by the locals trying to do some protection. And at some locations it goes actually all the way to the waterline. So here we have no beach left, right? We discussed that. So this is a long shore structure, which is, if the stone sizes are designed correctly for the waves events that we can expect here, then this is like a non-erodible component in terms of sediment transport. And then this is the tip there in the south. A very dynamic sort of sandbar that extends southwards, and that changes appearance all the time. So at the site visit, then also it's a preliminary design. That's important to say. So it's a sort of high level assessment of the different solutions. As part of the site's visit, we also took some sediment samples for detailed design, having a bit more elaborated sediment samples, and also a local bathymetry would certainly be a part. But at that preliminary stage, we just took a few samples on the beach. We established the sand, those size distributions, and then with that, you can compute the equilibrium profiles. You've also already seen that. So for the three locations, the equilibrium profiles, which will come in handy later. Again, we set up the spectral wave model. Inner waters, this time an open boundary, where we actually also included wave energy from a regional model. We are down here. It is mainly still wind-driven, wind-generated waves from two characteristic directions, one from the east, from the southwest. So the input of energy here is of limited value, but you might as well, or relevance, but you might as well include it. And then a very high resolution to resolve, as you can see, the wave transformation around these contours here. It goes down to 4 to 1 meter, and on the south it's a bit steeper. And then here that bar sort of extends. And that's exactly now the one point of discussion where the spectral wave model and the wave transformation that is available in the hydrodynamic modeling of the LitPack have both their strengths and their weaknesses. So the spectral wave model has some formulations for braking, etc., but it's all sort of on source term base.
Excuse me, Henry. Can you zoom more to this headland?
Yes.
Try to zoom more, such as we can watch more details.
Yes. Sorry. Of course.
Yes, please.
So we have the headland down here, and here on the south we go from 11 meters quite steep to 0, whereas here we go 8 meters, 9 meters, quite long out, almost 2 kilometers. And as I said before, the spectral wave model and the hydrodynamic model in the LitPack, they have both their strengths and weaknesses. So in the LitPack, we have nonlinear wave transformation, but showing refraction and braking. But we don't have any 2D effects. We have no diffraction. So the change of direction of waves around structures and headlands. And that is clearly happening here, as we can see in a second when we look at 2 storm events. The spectral wave model, on the other hand, can model diffraction and also braking, etc., to some degree, but it does it on a wave statistics based. So basically, so the question is, how long should our profiles extend for the littoral for the LitPack modeling? Well, the one is they need to extend sufficiently enough to capture all longshore transport. Closing depth was one component, but it should also be checked. We will see that in a second. So, and we need to go long enough that the offshore wave conditions that we extract from SW are still valid. So if we extract in super shallow water, they will not be valid anymore. On the other hand, if we go offshore too long, then these wave conditions are assumed to be changing along the profile only due to depth impacts, but not due to 2D impacts due to the wave diffraction around this headland. So as you can see, whatever choice we make, we introduce simplifications and we make errors, and whatever we do, we can't win. But as I also said before, we can still derive some useful results. It's just that we need to be aware of these choices and what that means, and maybe run some sensitivities studies, extracting at different points, etc., etc. Looking now at 2 storm events, and I can zoom in again in the spectral wave model. So we're looking at the significant wave height and the wave direction. This is now a storm from the southwest, and we can clearly see the wave diffraction around the headland, and then later on the refraction where the waves are aligning with the coastline. So in the spectral wave model, all these processes are included, but the accuracy of the later in the very shallow water is limited. So again, now, if I now place a profile here, and I assume these wave conditions out here as the input to my littoral drift, then I will only transform those waves along my profile due to the shallow water effects, so the refraction, shoaling, and braking. I will not get this change in direction due to the diffraction. There's nothing we could do about it. The only alternative is to do a two-dimensional modeling, which has also its limitations because it's computationally heavy. Then maybe you can't run 10 years, and also it might not be justified compared to the other uncertainties that we have anyways. For example, we don't have high-resolution bathymetry data available. We only have 3 locations of sediment samples. So it is okay to have slight inaccuracies as long as we are aware of them. And then there is the other characteristic storm that we get at that site is the westerly storm. So here you can see for these storm conditions, it's perfectly fine to have profiles along the east coast, right? Sorry, maybe I said westerly before. It's of course a storm from east. So here it's perfectly fine to have the profiles here. When we assume offshore conditions here, then we just get the shallow water transformation along the profile. There is no diffraction happening here, right? The directions hardly changes, and it's probably due to refraction. But then we're making the mistake here on the southern coast, where we get heavy diffraction around this headland again, and which is also extending underwater. So your error that you're introducing in your model depends also on the conditions, and with that on the time. So if you model a 10-year time series for the littoral transport along here, the times dominated by easterly wave directions, you have probably less error than in the times from southerly directions and the other way around on that coast. And then just here some wave conditions in the south, where we don't get anything from the east, and then a point a little bit offshore on the east coast, where we still get wave conditions coming around that headland, and obviously mainly from the east. And then we still need to choose profiles. I mean, we have the tools that we have. We as engineers, we need to make an assessment. So we're choosing profiles, and we identified them like that. We chose different sections where sort of the contours or the orientation changes significantly. And to be honest, this is a little bit arbitrary. I mean, that's based off the experience of the engineer that's deciding it. Then the next one will place that in another way. Maybe you need to do some sensitivity studies, usually especially for preliminary design, as this one is. There is not the time. So you will probably in reality have a discussion with one or two of your colleagues, and then you end up placing these profiles, being aware of the problematics that I did explained before, like taking the P6 here now or the P4, right? How the direction due to diffraction changes along that profile is quite significant here. I can zoom in once again. So these profiles, we still want to assess how long we actually need to go out to capture the longshore profile transport. But a first guess was from the equilibrium, from the closure depth, we need to go out to the closure depth as a minimum, and we went even a little bit further out because the closure depth is a simplified model where we then put these profiles together and then run a first run to see how the longshore transport is distributed. Due to the steeper slopes here, our initial profiles are already much shorter. And then the next step is to establish those profiles. And there we have some terrain data, we have some offshore data, but then we have a gap. We have a theoretical profile, the orange. I can zoom into this one again. We have the theoretical profile, the orange one, which was established from the nearest sediment sample. Again, profile 8 might be quite far away from that nearest sediment sample, so we're also having some error here. But then I need to somehow bring that together with my offshore. What we did here is now we fitted the equilibrium profile to meet the offshore bathymetry 100 meters off the coast. That's one way of doing it. And you can with that argue, okay, the sediment that we found on the beach might not continue offshore. And Another way of doing it would be to go down to the depth of that offshore and then connect it in a straight line, arguing, yeah, maybe there is that sediment and then it hits a non-erodible layer, and that's why it continues so shallow offshore. That's again things that we don't know and that we can perform sensitivity studies and then make a judgment of how important these or in what range the impacts of these simplifications can lie. Again, preliminary design in this case. So unfortunately, limited time and budget, you sometimes then also need to make calls and continue and follow, go all the way of your study to get a first idea of what is feasible and what not, and then revisit that later to refine. For example, with a local bathymetry, which was one of the recommendations also of our study here. We need a local bathymetry to improve our modeling. The question, okay, how far do we need to go out offshore? Usually, if you have, and that's actually, I think, true for large sections of the Egyptian coast, if you don't have this heavy diffractions, though you also sometimes have headlands, but if you're somewhere where you don't have the heavy diffractions, you can rather go a little bit further offshore on the safe side, and you rely on the wave transformation along the profile. Here, the thing was, as I discussed before, the further we go offshore, the more we introduce an error due to the not present sheltering effect in the littoral drift module, hydrodynamic model. So in that case, we took the profiles and modeled the extreme wave event, so the largest wave event that we have in our 10-year record, and look then at the profile, at the distribution of the longshore transport, and then you can see it approaches zero. So somewhere around here, if the largest event is not giving any transport here, then we don't need to take that. Then we don't need to model this part here in our littoral drift module, right? Then we can make that profile shorter and use our offshore wave conditions in this location, reducing a little bit the error that we're making due to the non-present diffraction in the rest of the profile. So that's a very useful assessment to make, to see how far offshore do we need to go with our profile. We again did the Q alpha curves, and you can see for the eastern coast, there's about 30 degrees difference between the current orientation and the equilibrium orientation. So again, it's probably pushing a little bit the limits of achieving an equilibrium profile. On the southern coast, it's a bit closer. So with a smart positioning of some structures, maybe we can locally achieve equilibrium profile and sort of stop a chronic erosion. Whereas on the eastern coast, even with our sand motor, our beach nourishment, or whatever solutions we come up with, it will require maintenance. And then we did not use the coastline evolution module. And why did we not use the coastline evolution module? Well, the one thing is, well, we could have set it up maybe in 2 sections, but clearly you cannot model the transport along this headland, right? I mean, there's a bar underwater extending, like you have some opportunities to model local structures, like the local interruption or the local effects on longshore transport in the coastline evolution module, but you certainly outside the box where the coastline overall follows a baseline. That's the one reason. The other reason is the huge amount of small structures here. So for every single structure here, the longshore transport doesn't re-establish anymore. So if you wanted to model this in a coastline evolution, you would have to somehow include the effect of these here as a longshore structure, like some form of revetment. But then how do you what parameters do you choose? Like how, so basically we pretty soon decided that we're too little in control of the output of what would come out of a coastline evolution model. And another main one is that again we're modeling potential transport, right? We have that assumption that all the transport is available, but that's also not the case because there are some non-erodible layers here. But you still have the results of all the lit line profiles, and you can post-process those. You have, for example, the net transport, and you can just plot them, and you can from that do some manual calculations, right? How do I zoom out again? So if we zoom into the other one, another result is the transport rates, and that's yearly transport rates in the northern and in the southern direction. And from the net transports, you can also compute differences, right? You can from the net, and that's the total transports along the profile. So that's what we saw before. So accumulated along the profile. And then just from the differences between the profiles, you can compute these, compute the differences. And then you can still see that the balance of the potential transport will be minus 1,500 cubes. I don't know the time unit now. So there will be some erosion here in that area if the material is available. If there's a non-erodible layer, there will not be any erosion. So it doesn't make sense to model this with a coastline evolution toolbox. Here will be material deposited. So basically from that post-processing, you can do a lot of sediment balance calculations. So we can, and that's last slide.
Please, I would like to make more details about why we cannot use coastline evolution. You mentioned that there are a lot of structures, but yes. I didn't notice where this is structure in this shoreline. This is number one. And there are other purposes you mentioned. So I hope you can focus more, give more details about why we cannot use the coastline evolution in this case.
Yeah, I can try to go on to that a little bit more. So, I mean, the one was around the headland, right? It cannot be modeled around the headland, but a solution, because we are the model formulation of the coastline evolution assumes a baseline and a more or less parallel shoreline and contours with that baseline. So that's clearly broken going around the headland. That part we could solve by assuming this here as a subsystem and this as a subsystem and setting up two coastline evolution models. So that one we could solve. But then the other one, there's a few other components that we can't solve. And the one is that we have potential transport that is much larger than the available transport, because there is in this area here, there are some non-erodible clay layers. So when we place a sand motor, placing a large amount of sand here or beach nourishment, that will be, these transport rates will be reached for some amount of time, but the moment the sand motor is empty or the beach nourishment is empty, it is not correct anymore. And that's difficult to include correctly in the coastline evolution module, because these the way the profiles are just shifted offshore and onshore, it's not displaying it to that detail of where then and how the sand is distributed in any way. The second component was all these small structures here. I don't know if it's a bit of an arbitrary recommendation, but you can find in the documentation of the coastline evolution toolbox that you should have sort of up to 20 structures is what you should maximum include in a coastline evolution. And the distance between those structures should be such that the longshore transport sort of can re-establish again, so that you have that's for the groins, that you have a local distribution of a local disturbance of the longshore transport. That is not the case here because we have so many structures. So you could then also, the alternative is that instead of modeling all these groins here, you say, okay, we have actually a revetment. So we have a structure along the shore where the effect is that it stops the shoreline erosion due to that revetment. But then you need to find the parameters to model that revetment, and that would mean that you somehow need to have some knowledge of the exact long-term effect of these groins here to then compare that with the long-term effect that you end up modeling with a revetment in your model. And we simply didn't have that information. So we could model more details, but we basically didn't know how to, or we didn't have the information to feed the model with the additional input, and then also to compare it with our ground data. And the last one is that the symmetry was very uncertain in these shallow water areas. So basically, all the list of these together, that we decided that in the preliminary design phase for this project, there was no added value with setting up a coastline evolution module, that we could achieve or we could get the same answers by doing, let's say, housekeeping computations based on the outputs from the individual profiles. And being then, of course, that's more simplified because we just look at differences between those profiles. It's more simplified, and we don't know how then this sand here would develop, would distribute, etc. But it's sort of acknowledging the level of detail and the level of confidence of our input data that we had in that current situation. And it was also sufficient to then combine with the experience of our coastal team to assess different solutions and design alternatives. So for example, you can sort of, as a back on the envelope, if you place a volume of sand here, you can, just as a pure post-processing step, compute for how long that would last, how it roughly would be distributed along your coast. Yeah. And then an alternative, we came up with a lot of alternatives. I can't show them all, but then one of the alternatives was to place a beach nourishment rather along the shore and have a small structure here, because there are some individual events. And by the way, that's why we decided to model the 10 years as a time series rather than as in a scatter approach, so that you had also a time series available of these longshore transports of the 10 years, and you could sort of zoom into peak events. And from that, we found that there are some events where you have also a rather strong transport in the southern direction. So if you get such an event immediately after the sand was placed here, you would sort of lose a large quantity of that sand motor. So the long-term distribution of the sand northward would never happen if you're unlucky and you have such an event immediately after placing it. So that's where then this alternative solution came in, so that the similar quantities are placed directly along the beach, and then you have a small structure here which can hopefully stop a little bit of a disappearance of sediment in case of a northerly event. The problem with that one is very practical. Actually, you have very shallow water here, so it will be difficult to come in with barges, or you will have to use very small barges to get the material here, and the access from the shore is also not straightforward with large working machineries, because some of the residential properties, they go right to the edge, which is one of the advantages of doing it like that. Yeah, you can come in with a barge in fairly deep water and place a large material in this area. So there's a lot of components between practical aspects, what can be done, what modeling components do we have, to what extent, to what detail can we model with the data that we have. Doing a preliminary design and some feasibility studies, deciding then probably the next step will now be we proposed 8 alternatives as a result of that project that was actually completed just here in summer. So now it goes back to the municipalities. They look at, there will be these different solutions come at different cost, at different maintenance requirements, etc., etc. So they will now narrow it down, and then we go further into the details. We will, as I said before, we will collect bathymetry data. We probably collect some more extensive sediment information. And as we zoom into the details, we might be then in the next iteration use other models. We might in the next iteration set up a coastline evolution model, or maybe even some 2D modeling around this headland, so outside the LitPack suit, which then will only be for individual events, right? We can't model the whole thing in 2D for 10 years. So maybe the final message is a little bit like, while in such a course, or also in the documentation and the user manuals, it's always also pointed in the direction that you need to critically judge your output. But still, you could get this idea of modeling as this linear workflow of, you find some input, you model, you get an output, you have a solution, right? But that's very much not the case. It's a very iterative process where you have to go back and forth a lot. And again, because of the large uncertainties, probably establish some monitoring. And with that, I'm at the end of my last project example. So to just quickly conclude, I try to give another big picture view of the different components available in the LitPack modeling suite, how the profiles are handled in a different way, like the profile evolution depth as a function of X and time versus the coastline evolution, where we have the one line model where a constant profile is shifted offshore and onshore. And then I gave 3 project examples where different components were used for various assessments. Yeah, and with that, I'm at the end. Maybe we have time for a few questions.
Thank you, Henrik, for your great presentation. It was very interesting, actually. And welcome for any questions regarding this presentation.
And otherwise, oh, sorry, was there a question? I didn't hear.
Excuse me?
No, was there? I didn't want to interrupt anyone. I just wanted to say, otherwise, if there's no immediate questions now, you also have the contact information, right?
Yes, great. هل في أسئلة دلوقتي عندكم شباب؟ أحمد عايز تقول حاجة؟ خلاص خلاص. Okay. Okay. Thank you, Henrik, for your presentation. And if we have any questions, we are going to send you through the email. Thank you again.
And then maybe we will meet then some of you for the advanced module. Is that correct, or is that another group of people?
We don't know yet.
Okay.
Some of them, sure, they will continue with us in the advanced course. Sure. In the advanced training, we are going to select some of the trainee now.
Great. Okay, thanks everyone for your attention, and good luck for enjoy your last day, and bye for now.
Thank you very much. Bye bye. Bye. الحقيقه كان جميل قوي البرزنتيشن، كانت قيمه، كانت سريعه، بنتكلم عن براكتيكال بروجكتس which is very complicated. وهو الراجل بيقول يعني احنا يعني بنيجي في مرحله ما مش عارفين بنعرف نيجي والمواضيع بتبقى اوبن بروبلمز، يعني مفيش ديسيشن سهل واضح. زي ما بقول لك سيجمنت موضوع معقد يعني فيري كومبليكيتد. السلام عليكم. يمكن لا بس
انا مش فاهمه
ايه
مش فاهمه ايه يعني ده كان بيحسبه ازاي؟ اليد دي بيحسبها يعني
ليه؟
عامل شكل كده بتاع اليد ده اللي معاهم بي 1 وبي 2 وبي 3 حاسب اليد حاسبها منين؟
حاسب اليد؟
ايه
ما هو اللي حصل زي المشروع بتاعنا في مصر. هو حسب الدريفت على كروس سكشنز، هو خد شويه بروفايلز كتير يعني شويه بتاع 10 مثلا حاجه. 13 13 ما تقولش معايا. اوكي فواحد 13 بروفايل عشان خاطر كيس، وكل بروفايل حسب الدريفت بتاعه. فطلع ارقام، فده طلع 20000 وده طلع 200000 وده طلع 500 وده طلع. طيب وراح عمل ايه؟ ما بين تو سكسيسيف بروفايلز، ما بين كل اثنين، من الناحيه دي داخل 10 ومن الناحيه دي طالع 20، اذا هنا بفقد 10. اذا الحته دي في الشور لاين فيها لوسز 10 متر كيوبيك بير مش عارف متر واخد بالك بير يير. اذا هنا احنا في لوسز وهنا في لوسز وهنا في بوزيتيف وهنا في بوزيتيف. فالاريا اللي انت شايفاها دي اللي هي ما بين every two successive profiles there are a net sediment loss or a net sediment gain. واخد بالك؟ ده الاوتبوت اللي كان بيوضحه. المشكله الكبيره في الموديل بتاع المنطقه. اول حاجه طبعا انا كنت عايز ادسكس مع بس يعني الموضوع حلو يعني، بس ما كنتش عايز اطول عليكم يعني. الاس دبليو هو استخدم اس دبليو، والاس دبليو ما دخلش ديفراكشن، هو قال يعني يجي تيك ديفراكشن في الاكونت. فالمشكله ان انت عندك هيلاند كده اهو، اللي جاي من هنا بيعمل منلي هنا ديفراكشن، واللي جاي من هنا منلي هنا ديفراكشن.